Today we're going to talk about endothermic and exothermic reactions, and this can be found in section 9.4 in your textbook. So what is an endothermic or exothermic reaction? So whether a reaction absorbs or releases heat as it occurs tells you whether it's endothermic or exothermic, and this property is called enthalpy. Okay, and this is one of the components of thermodynamics that we're going to talk about in this chapter. So an exothermic reaction is one where there is a net release of energy. So that means that as this reaction happens, overall, when you break bonds and then reform bonds, there's extra energy that is released. So an exothermic reaction will actually feel warm when it occurs if you hold the test tube in your hand. An endothermic reaction is one in which there is a net absorption of energy. So if you were to hold an endothermic reaction in your hand as it's occurring, the test tube would actually feel cold because it's pulling energy from its surroundings, from the test tube, from your fingers, from the air around, in order to get the energy that it needs to break the bonds. Now we talked a little bit in previous chapters about how bonds contain energy. So chemical bonds are actually one form of potential energy because there's energy stored in them. So what that means is that if you're going to break a chemical bond, it's going to require energy, and if you are going to form a bond, then that will release energy. So the bond energy, which are listed, some of them are listed in this table, and there's a similar table in your notes, they tell you how much energy it's going to require to break that particular bond, or how much energy will be released if we form that particular bond. So we're going to do a couple of examples that show how these bond energies can tell us whether a reaction is going to be endothermic or exothermic. Okay, so the first example I have here is an exothermic reaction. In this reaction here, we have two H2s, so we have H bonded to H twice, and we have an O2. And if you remember, O2 is O with a double bond. And it makes two water molecules, which is going to look like this. Okay, so first we need to figure out how much energy is absorbed if we're going to break bonds in our reactants. So this is only going to be the stuff that is on the left side of our arrow. So we have two HH bonds, and you can look at your table and see that one hydrogen bond is 436 kilojoules of energy. Okay, so we'll have to that number times 2 because we have two hydrogen bonds. And then we have one oxygen-oxygen double bond, and an oxygen-oxygen double bond is 498 kilocalories per mole. So that's how much energy will be required to break all of the bonds in our reactants. And then if we, similarly on our products, if we calculate how much energy we're going to get back when we reform bonds, in this case we have 4 of exactly the same bond. We have an OH bond here, 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 and here. So if we look at our table, an OH bond is 464 kilojoules per mole. Okay, so we're going to get back that amount of energy times 4 for each of those bonds. Now, if we add that up, that gives us a total of 1,370 kilojoules per mole absorbed and 1,856 kilojoules per mole released. So the net energy of our reaction, in this case, we've released more heat than we've absorbed. So in terms of net energy, that tells us that in total, if we do 1856 minus 1370, that we've released 486 kilojoules of energy per mole of reaction. And so if your net energy is released, then that would be an exothermic reaction. So again, a release of energy would mean that that reaction would actually feel warm if you were to touch it when it was occurring. Now let's do an example where we have an endothermic reaction. So in this reaction we have one N2. So if you remember back from when we did Lewis structures, N2 is just at two ends with a triple bond in between them. And we have an O2, which we just did on the last side, and there's a double bond between those. And they become two NO molecules. And these have free radicals. We're not going to really cover them. Just know that there's a double bond between the nitrogen and the oxygen. So the energy absorbed to break the bonds in the reactant, so we need to add up all the bonds that we have on the left side of our equation. So one nitrogen-nitrogen triple bond is 946 kilojoules per mole. And then we're going to add to that the oxygen-oxygen double bond, which is 498. So that gives us a total of 1,444 kilojoules per mole of energy that's absorbed in order to break those bonds. All right. Now, if we look at the energy that was released when we reformed new bonds in the products, we have two NO double bonds. So those are 631 kilojoules a piece. And so we have two of those because we have two molecules. And that gives us a total of 1,262 kilojoules per mole. So our net energy for this reaction is going to be energy absorbed because our energy absorbed is bigger than our energy released. And so we're still going to subtract the two. So if we subtract them, we get 182 kilojoules per mole. And in this case, it's going to be of energy absorbed instead of energy released. And that is because this is an endothermic reaction and it takes more energy to break the bonds than we get back when we reform bonds in the product. All right, so this concludes our discussion of endothermic versus exothermic. We'll talk a little bit more about energy in reactions in our next video in both the first and second laws of thermodynamics and how energy gets redistributed in chemical reactions.